So in chapter 5 here, we're talking about quadratics. In section 1, we're going to look at what a quadratic is and how to use a calculator to find a quadratic equation with some data. And we're also going to calculate some equations ourselves using methods we already learned. So, there's a little intro here. The ubiquitous parabola, meaning that everywhere you look in the world, you can see parabolas if you know what you're looking at. You got a big one downtown. You got one out here at Six Flags. Parabolic shapes shown at the. Excuse me.
What ride is that?
I don't know. I don't know if that's even Six Flags. That's just a roller coaster ride. I think we have the Arc de Triomphe here in Paris.
Looks like the Eiffel Tower.
Maybe it's the Eiffel Tower instead. I'm not sure which of those two. Arches and architecture everywhere have parabolic shapes. This satellite dish is actually a three-dimensional parabola. And what's cool about it is that when rays come in and bounce off a parabola, they go straight to a receptor, which then deciphers a signal. And parabolas are used, all kinds of ways in the world. Is the point here? Even gravity. If a fish jumps up and goes back in the water, even gravity acts in a parabolic way. So quadratic equations, you may know from physics class, quadratics will fit gravity questions. Some previous knowledge, okay? It's supposed to be a close on that parentheses back there. So we got the equation y equals x minus 2, absolute value of x minus 2 minus 4. You remember back in chapter 2, we we're graphing those. These kind of equations have a vertex, they have symmetry points, they have an axis of symmetry, and we also could talk more about linear equations. That's other stuff we've done this year. But the main thing right now is remembering what these absolute value equations look like. Okay? We have a V shape here with a vertex at where? 2, negative 4, right? Pardon me? The graph has an axis of symmetry at 2. Remember that? X equals 2 is that axis of symmetry. And we have what's called symmetry points at here 0, negative 2, and 4, negative 2. Remember those called symmetry points on the graph? Okay. You're going to see the same things happening with parabolas. Okay? For example, go ahead and do that. Identify the vertex, axis of symmetry, and corresponding points for both of these. Okay? A vertex at what point? How about Billy giving me a vertex here, part A? 1, negative 1. Now, Q, the point Q right here has a symmetry point over here. We're going to call it Q prime. Q prime is what point? How about you? Origin, 0, 0. So Q is here, Q prime is here. P has a symmetry point over here called P prime. This is a symbol for prime if you don't know. P prime is, how about it, 7?
3, 3.
Over 3, up 3, good. 3, 3, good. And similarly with the other graph, we have a vertex there at negative 1, 2. Symmetry points P prime at where? P prime, where's it, Sam?
0, 1.
Right here at 0, 1. And Q prime over here is at, how about it, McKenzie?
-3, -2.
-3, -2. All right. So, pretty easy so far, right? So very similar to absolute value graphs, only these have more, notice that we're using more points to graph this because you need more points for a curve. Yes?
So points corresponding to like others would just be on the opposite side of it?
Yep. Points corresponding to a particular point, they're called symmetry points, are the other side of the axis of symmetry. There's the axis of symmetry. They're equidistant from that axis of symmetry. The axis in this case again, x equals 1, that vertical line through there. And the one over here, axis of symmetry, x equals -1. Okay, onward and upward. So quadratics generally follow this form with a square term, a linear term, and a constant term. A square term, a linear term, and a constant term. Whoops. Okay? So if there's no square term, it can't be a quadratic. Can there be a missing linear term and still be a quadratic?
Yeah.
Sure. Or the constant term could be missing. But if it has a square term as its highest power, then it is a quadratic. So there's some little practice problems here with these where we actually have to simplify. If you simplify this part A, make it y equals, you take it out of function notation. There's nothing to do inside that parentheses, so we just remove the parentheses and put together like terms. And when we do that, we can see it's no longer a quadratic. This is a linear function. So it's a linear function. And it has linear term of 5x. You're supposed to identify a quadratic, linear, and constant terms now. So if we identify the linear term, there's no quadratic term. None. The linear term, 5x. The constant term, well, we can say 0 here. We can assume 0 is the y-intercept there, right? So 0 is the constant term. All right. Now, in part B, we're going to have to do what?
Foil.
Remember the old term foil? In Algebra 1, maybe? Hopefully you saw that.
Yep.
How do we do foil here? Tell me, John.
Like first, outer, inner, last.
First, outer, inner,
Yeah.
last, like that. Okay. And when we multiply first terms, we get
3x squared.
3x squared.
outside, John, keep going.
1x.
Negative, right?
Yeah, negative. And then 15x.
Negative there again.
And then negative. And then 5.
Plus 5, okay? And there's usually some like terms to put together. So we've got y equals 3x squared minus 16x plus 5. This is obviously what kind of function? Quadratic, okay? First of all, it's a quadratic function because of the square. The quadratic, linear, and constant terms.
Quadratic would be 3x squared.
Good.
Linear would be negative 16x.
And constant,
Would be 5.
5, good. So, again, pretty much some old Algebra 1 stuff here, but we're having to identify a quadratic function and its terms. Okay? Let's put the video on stop there. How many minutes is it? Is up?
10.
10? Okay, let's put